Welcome to this video about scripting your own custom model with the LISEM software. Today we're going to look at how you can make your own custom-made visibility-based models to capture the dynamics of natural hazards. To get started, again we've opened LISEM and you see on the left we have the map viewer, on the right we have the user interface. If we go to the script tab, you can see I already have a simulation script open. So we'll try to run this and we go through what each of the lines of code actually does. So let's look at the data I have in my working directory first. So there's two maps here, one called test M5, which is an elevation model, and initial fluid height 2, which is a water height for the start of the simulation. If we double click this, it opens and we can see we have some kind of lake, some reservoir, and some area for runout. This is just a hypothetical test scenario. After this, we'll look at a more realistic simulation of flow. Just to visualize this a little bit better, we make it a hill shade and we can have a look in 3D to see what's actually happening with the data. So we have a big reservoir and a runout area where the water can actually flow to. Now let's go back to our normal view, zoom to extend. Okay, so let's look at the script. As always, we start with our void main. Our main function is our entry point, and when we start the script, this is where the script actually starts executing code. Then we create a new variable where we load the elevation model. So we can load any data format, any raster-based format. In this case, it's a map file, but it could be geotiff anyway. We load the map into a variable called m. In the second line of interest, we actually load the water height. We call that WH initial, the initial water height for our simulation. The third map we need for our flow simulation is Manning surface roughness coefficient. So this determines the strength of the frictional force at the interface between the water and the surface. Here we're going to estimate that everywhere this will be a value of 0.1. Typically you would let this depend on the land use, but that's something we'll look at in the next example. We don't have a need for any soil parameters at the moment. We don't do infiltration. Again, next simulation will add that. Then we define a list of 3 maps. So a list is defined with the type array, and the array contains maps. And the list contains 3 maps. So the first one of these is the initial water height. Then we have our velocity in the x direction, which we'll set to 0. We start with the 0 velocity. And the velocity in the y direction, which is again set as a 0 map. The reason we set the initial velocity to 0 is because we start with a steady state lake. It's sort of a dam breach scenario, if you will. Of course, you can start with any velocity you like. And these are maps, so they can be different velocities at different locations. Now these 3 maps, the water height, velocity in the x and the y directions, that determines the entire state of the simulation. The state of the flow, if you will. So the height and the x and the y component of the velocity is what we are going to progress through time. Now before we start actually to do the simulation, we add some information to the map viewer. So here I add a layer called WH, but let me give that a bit better name called water height, and the other one we'll call velocity. So these are 2 view layers. I have this function add view layer, which I can use to add these layers to the map viewer. And later we'll update the data to them dynamically. So far that's all been set up. We've loaded the data. We had 2 maps, the elevation model and the initial water height. Manning's n we estimated as a constant value. And we defined our flow property list. Now we are going to actually do the simulation itself. So if we look at the following lines, line 21, 22, you see that we do a loop, a for loop. In this case, I'm going to iterate with a variable I, and it goes from 0 to 5,000, which means I do 5,000 time steps. Now, 5,000 might be too many. In my case, I'm just going to visually see whether the simulation is done and stop it if needed. Then I estimate my time, and that depends, of course, on the time step. Now, in our case, we're going to take a time step of 0.2 seconds, because that makes for a stable simulation. That's mostly trial and error, but that depends also a bit on how you estimate the velocities as opposed to the grid cell size. Here we have a cell size, I believe, of 10 meters, with velocities also of probably around 10, a bit more perhaps, meters per second. So that means we have to think in time steps of about 1 second, a little bit less to be safe. Next is the actual simulation code itself. So within LISEM, there's a lot of functions available that do the simulation of different natural hazards. So for water flow, for tsunami flow, for debris flows, etc., etc. And all of these functions can be found in the toolbox. So if you look, for example, flow, you see many different types of models. Flow for dynamic with suspended transport, flow dynamic, which is a dynamic flow model for water, based on the Saint-Fernand depth average equations. Flow debris, which is a two-phase solid fluid mixture model for debris flows and landslides. Flow tsunami for tsunamis, etc. So if you want more information about the function and the arguments and what it does, you can also look in the toolbox. Here we're using the flow dynamic. So the flow dynamic is a version of the Saint-Fernand depth average flow models for surface water flow. And this model takes into account gravity, friction, inertia, and is basically the standard flood model that's used around the world. So the way that we use it, we put in the elevation model, we put in the Manning's N, and then we put in our flow properties. So the first one, the water height, the x velocity, y velocity, and then our time step in seconds. Note that all of the variables we've discussed so far have all been in metric units: meters, seconds, meter per second, etc., etc. The function returns for us the updated flow properties. So if we started out with the flow properties at time equals 0, now we end up with the flow properties at time equals 0.2. And the next iteration, when we come across this code again, it's going to go from time equals 0.2 to the flow properties at time equals 0.4. Finally, if we have the new flow properties, we're going to replace the data in the map viewer. So the first variable L is a UI layer, and that contains the water height, so we put the first flow property in there. The second one contains the velocity. Now, we work for the flow state, we work with the x and y velocity in their independent components, but we can get the total actual magnitude of the velocity by using some Pythagoras theorem. So we take the square root of the x component squared plus the y component squared. And in the final line, we actually print the time step that we have just finished, just as some information that the model is running. So that's it, our script is pretty much done, and we're ready to run this. Now, this goes quite rapid because this is a small simulation, so I will run it in pause so we can actually see a little bit what's going on. So a lot happened already quite a way. Let's have a look actually what's happening here. So I have my layers that have been added now in the map viewer. We can see those. We have the velocity and we have the water height. So for now, I'll leave the velocity. You see we have a water height. I might give that a little more appropriate color and put a hill shade underneath. So what happened here? We have our lake and we see there's some kind of wave forming in the lake, and here water is flowing out. Well, that wave makes sense because our initial water height also had an elevated bump in there, just to see the wave behavior. Now I'm going to remove that one. If we now continue the simulation, we can actually see what's happening. So the waves progress and bounce, you get this standing wave within the lake, the water flows out and it fills the other area on the right. So this gives us a very simple flood simulation scenario. Of course, you can make this more complex with detailed information on Manning's surface roughness based on land use, more accurate topography of a real area, and that's something we'll look at now. For now, first I will stop the script. For those that are interested, it's also sometimes useful to look at the data in 3D, and we can also do that with water flow. So if I go to the 3D version, and let's say I want to have this layer as more water-based colors, and I can actually set it to be a transparent water-like layer. So if I go to Style, and I set is surface and is flow surface, it draws the actual layer as a water-based layer. So if we go back to style and we set it back to being drawn normally, we get back our original data view. Okay, so far for our first scenario. Let's look at a second one. Remove these layers, and then we move on to the second simulation. So the second simulation is similar to the first one in the sense that the script looks very similar, but it's a bit more extensive. There's some additional processes happening. So let's have a look at these processes and see what data is required for them. If we have a look at the script itself, we see that it starts off very similar. We have our void main, our entry point for the function. Then you have our elevation model, our initial water height, Manning's N. So our initial water height here is actually an empty map containing only zeros because we want to do, in this case, hydrology induced flooding. And Manning's N is actually a map. So let us find that one and open it. So these are the Manning's N values, and as you can see, these are based on the land use, land cover combination. So these are estimated based on literature values and then filled in for each of the different classes in the land use, land cover map. So for example, for buildings and urban areas, you see we have a very low Manning's N because the surface roughness of concrete and compacted dirt is actually quite low. And in forested areas, we see we have the highest value for Manning's N. Okay, so
Hello.
hello.
Oh.
So once we have our Manning's N values, we go on and we see one of the next ones is called WF, the wetting front. Now this is a new parameter that we haven't seen before. And the wetting front is used for the infiltration modeling. Now, within the LISEM code, there's also an infiltration model available, and this infiltration model is the green and empt infiltration model. And this is one of the more standard infiltration models used around the world. For this infiltration model, you need to know the depth of the soil, you need to know the porosity, the initial moisture, and also the depth of the wetting front at the start. I won't go into more detail about the workings of the green and empt model, and more information can be found online. So here we have the parameters that you need. The initial depth, and generally it's good practice to have some very minor initial depth to avoid numerical errors. Psi is the metric suction in meter equivalent water pressure. Theta is our initial water content, so that's between 0 and 1 as a fraction. And theta S is our porosity, so that's the porosity of the soil, also between 0 and 1. So if we look at one of those parameters, you see that theta S is mostly homogeneous in the area at 45.3%. These parameters were actually calculated within the LISEM model using statistical relationships based on the soil texture. And the soil texture was derived from a soil texture map. If you were more interested in that, you can also look at the Saxton functions based on the work of Saxton et al. In 2006, who did a large study on statistics of soil texture and related physical parameters. And you can use those to estimate the saturated conductivity, estimate the porosity, field capacity, etc. Finally, you have the soil depth, and soil depth was estimated using physically based soil depth modeling. The unit here is actually in millimeters, so I need to convert that to meters because all of our inputs are in metric units. So dividing by 1,000 should give us the right conversion from millimeters to meters. And we see we successfully converted it to meters depth. Now, just like we did in the script before, we initiate a list of flow properties, our water height, which is 0, and the velocities, which are 0 at the start of the simulation, because the rainfall hasn't started yet. Then we have our infiltration. This is also a list of flow properties, and they are the wetting front depth and the water height above the surface. Note that the water height above the surface is present here in the first part of the flow properties list, and also the last one in the infiltration properties list. So we have to keep updating them from the one list to the other. We add some view layers like we did before, and we start the iteration, the time loop. Now again, I suggest we work with a time step of 0.2 seconds. So we also fill it in the flow dynamic function. We estimate the rainfall, which is actually based on a triangular rainfall curve. So to do something like that, so in line 41, we actually estimate our precipitation. So the rainfall rate that's being added at a certain point is actually based on a triangular rainfall curve here. In reality, typically we use actual measured precipitation or forecasted precipitation, but in this case it's a little bit complex to add that directly from a table. So instead we have this example with triangular rainfall. So in line 41, we actually add a rainfall to the simulation. So we estimate the rainfall based on a triangular curve. Typically in real simulations we add from a table the measured or forecasted precipitation, but in engineering practice the triangular curve is also often used. In line 44, we take the flow height and we add a rainfall to it. Then we're going to do the flow simulation like we did before. We provide the elevation model, Manning's N, the flow properties, the height and the velocities in x and y direction, and the time step. And we use that to update our flow properties. So now we're also going to model infiltration. And to do that, we have to first update the flow height in the infiltration list. So we had our infiltration property list, the wetting front and the water height. We have to update the water height. So the second one in the infiltration list is the first one from the flow properties list. Then we do our infiltration model. Again, there's a simple function for this, green and empt. We provide the flow properties, soil depth, saturated conductivity, the porosity, the water content, the metric suction, and the time step, 0.2 seconds. And we get back a new infiltration property list. So the updated wetting front and the updated water height. So the water height will be lower, of course, because water infiltrated, and the wetting front will be higher, deeper into the soil. Is more accurate. And then we take the water height that we have from the infiltration list and update our normal flow height. So they are actually identical again. Well, finally we update the data in the map viewer and we print the current time step to the output window to make sure that we can see where we are. Okay, so that's mostly the working of this simple hydrology-based flood script. Based off rainfall and an infiltration process and runoff, this will simulate flash flood processes in a catchment. Let's actually try to run this. So we're going to press run, and I'm going to clean up a little bit the interface because I had quite some maps open. And personally, I like to put a hill shaded relief under my simulation so I can see a little bit what's happening. And make the water a little bit blue. So we can see after the first time step, for some areas there's no water at all, and some areas you see some water has already started to form. Now this is very little water. I will make the text a little bit bigger so it's actually readable, but we're talking here about 1 times 10 to the power minus 8. So this is after couple seconds, you see that there's still very little water on the surface. The rainfall event has barely started and the simulation also has to still continue for a bit. Why we see these patterns, of course, then is because of the differences in infiltration rate. For some areas the infiltration can actually manage, and for some other areas the infiltration is not able to cope with the amount of rainfall, and runoff has already started. But since it is very little, it's not converging significantly. So this will take a while before the simulation is actually completed. The water will converge, flash floods will form, and eventually flood intensity will be the result. Now let's say we want to make some customizations to the script because we want to get out some more information. Let's go back to the lake example and have a simple manipulation and try to get out the maximum flow height. So to do that, first we'll keep track of the maximum flow height we've seen so far. Well, at the start, the maximum flow height we've seen so far is actually 0. So we'll call it WH max, and we initialize it with dam times 0. And then in the loop, we're going to update that and say our water height max is equal to the maximum of water height max and flow drops 0. So this is going to say my new value is either the old value or the current flow height based on whichever is greater. And we can actually store that to disk. So say water height max dot tiff is equal to water height max. Let's save these changes and I actually run it. And oh, I made a spelling mistake, no matching symbol flow prop. So flow prop was not recognized, and that's correct because I'm missing the letter S at the end. Oh, and I see my working directory is not set correctly. Here it is, so now it should be able to find the actual maps. And let's zoom really quickly to the area. Yes, there we are. The simulation is running. And let's stop it and see what is actually there. Yes, so this is our maximum flow height during the simulation. So you see exactly how the wave propagated and where and what height the wave actually reached. So something like this is very useful for tsunami modeling, which is also possible in LISEM. For watching this video, I hope it was useful and helps you create some custom models using the LISEM software. If you want more information, you can always find it at lisemmodel.com or contact us by email. Thank you very much.